In this video, I introduce a COM for action generation in text-based games. A text-based game is an electronic game that relies on text to convey information and receive player input as an action. Contextual Action Language Model generates a complex set of action candidates conditioned on the context. Reinforcement learning agent re-ranks the generated action candidates to maximize the reward of action to the environment by using the deep reinforced relevance network. As shown here, this is COM workflow. This is context. COM is used to reduce the action space and then get a small set of action candidates. Reinforcement learning agent use this observation and action candidates to re-rank the actions and find the best action. A text-based game can be formally specified as a partially observable Markov decision process, where a player issues a text action A and receives text observation O and the scalar reward R at each step. Positive rewards are received for solving key puzzles, and negative rewards for dying. Gamma is a future reward discount factor. Latent state S contains the current game information, which is only partially reflected in observation O. The transition function S prime specifies how action A is applied on a state S, and then the state transits from the current state S to the future state S prime. A game agent uses reinforcement learning to learn Q network, where phi is parameters of the Q network. The agent encodes the observation O and each action candidate A using two separate encoders, FO and FA, and then aggregates the two representations to derive the Q value via a decoder G, as shown here. For learning phi, tuples of observation, action, reward, and the next observation are sampled from experience reply buffer to stabilize the model training. The temporal difference loss is defined as here and shown in this figure. During play game, softmax exploration policy is used to sample action, as shown here. When the action space A is large, the denominator is intractable here. COM uses the large language model to reduce the action space A and makes the learning tractable. Consider a database A with n trajectories, and each trajectory contains error observations and actions, as shown here. The cross-entropy loss is used to train the COM model, as shown here, where C is the context. Here we only use the previous observation and action. Since each action A is a multi-word phrase containing M tokens, the conditional probability P set in the formulation above can be written as here. The cross-entropy loss is used over each token AI in action A during training. A pre-trained large language model is fine-tuned on the dataset D, which models dependence between the context and the action in a flexible way. A bin search method is used to generate most likely actions. Though large language models are learn to generate useful actions, they are not optimized for gameplay performance. COM generates top key action candidates, ALM, given context C, and trains a DRRN to learn to function over the smaller action space ALM. This can be done by replacing A with ALM in the formulation above. In this way, COM generic action priors is combined with the ability of reinforcement learning to learn policies optimized for the gameplay. For more details, please check with these references. Thank you. Bye.